Hello, my name is Rishabh Baghel, and this work has been supervised by Professor Ravi Kiran from CVIT, IIIT Hyderabad. In this presentation, we introduce MeronymNet, a novel hierarchical approach for controllable part-based generation of multi-category objects using a single unified model. Let's begin with an overview of MeronymNet. Given an object category and an associated list of its parts, the first module stochastically generates part layout in terms of bounding boxes. The generated part layouts and category attributes are consumed by the second module to generate a dense part-based label map. Guided by category label, a final module translates this label map to finally generate the RGB object. Let's look at the modules one by one. We'll begin with the first module, which generates part bounding box layout. The part layout of an object is represented as a graph, whose nodes correspond to parts information about their existence within the object. The edges between nodes are based on predefined meronymic relationships between the parts. Here, meronymic is a linguistic term which represents part of relationship in semantic ontologies. Our graph-based part layout representation of the object helps capture the inter-part relationships in a compact yet rich manner. The generative model we use is a variational autoencoder. As part of the encoding stage, the part bounding box is processed by GCN layers, followed by a couple of linear transformations to obtain parameterized representations of the corresponding latent distribution. The latent distribution is conditioned on the object category and the associated list of its parts. A skip connection is also added, which assists gradient flow. The decoder stage of the VAE transforms the latent representation into components of the object's part bounding box graph, that is, the node matrix X and the adjacency matrix A. The reconstruction loss consists of three terms. In the first term, a binary cross entropy term penalizes part presence predictions, which disagree with the ground truth counterparts. To encourage coarse localization of individual bounding boxes, we use two instance level losses, mean squared error, and intersection over union between predicted and ground truth bounding boxes. To impose additional structural constraints, we also use a pairwise MSE loss defined in terms of distance between center of bounding box pairs. For edge metrics, we use binary cross entropy as the per element loss. Next, we'll look at label map VAE, which take part layout generated by box GCN VAE and category attributes to produce a dense part-based label map. Similar to the previous module, this is a variational autoencoder as well. The part masks are first scaled to the same size before encoding. This ensures that the range in part sizes does not affect quality of generated masks. The scaled part masks are encoded via convolutional layers. The resulting per part representations are aggregated using a recurrent network to obtain the object level representation. To also incorporate the layout aspects, the bounding boxes generated by previous module are also encoded in a similar fashion. The bounding boxes are encoding infused with the aggregated mask-based object encoding. This helps capture both local and global aspects of object geometry. The fused representation is processed by linear transformation to obtain parameterized representations of the corresponding latent distribution. Similar to the previous module, the latent space is conditioned but on object category and the aggregated bounding box representation in this case. In a manner that complements the encoding stage, the decoding stage of label map VAE transforms the latent representation into binary masks of the object as shown. The reinsertion loss is per pixel binary cross entropy averaged on a per mask basis and subsequently over part present in the object. Now we come to the final module, guided by the category label. The label to object module translates the label map obtained previously to finally generate the RGB object. We design label to object as a category conditioned variant of this paired architecture by Park et al. To encourage category-aware translation of label map into corresponding object, the one-hot category representation is appropriately transformed and concatenated with scaled label maps along the module pipeline as shown. Complementing our category-aware generator, the loss function features a category-aware discriminator as indicated above. We use the large-scale part-segmented object dataset, Pascal parts. This plot shows the density distribution of part counts and object instances for each category. The varying range and frequency of part occurrences across categories combined with the requirement of object generation form a single unified model, and it poses a lot of challenges. Let's look at the sample generations by MeronymNet. For each sample, the generated bounding box, the corresponding label mask, and the RGB object can be seen. Notice the diversity in number of parts, appearance, viewpoint among the generated objects. The generations here are for sheep. This is for person, motorbike, horse, airplane, bicycle, bird, dog, cat, and car. Let's look at some examples of interactive modifications enabled by MeronymNet. In the first scenario, we generate an object based on the user-specified category. If parts are not mentioned, a partless sample from the category's training set distribution is chosen. If the user chooses to add new parts and specifies them, the GUI allows the user to add the part masks. When user clicks render button, the augmented label map is processed by label to opt module to obtain the updated mask generation. A similar process flow allows the user to manipulate the object at bounding box level. This is especially useful for creating cartoon-like exaggerations, as shown in the examples. In another scenario, the user may specify desired edits at a higher level, for example, in terms of parts to be added or removed. The updated part list is subsequently used for generating the corresponding objects. Notice that the viewpoint for rendering the object has changed from the initial generation to accommodate the updated part list. This scenario especially demonstrates the MeronymNet's holistic part-based awareness of rendering viewpoints best suited for various part sizes. The above graphic represents our part-based object generation pipeline. The input and output entities are represented as blue circles. The red labels denote the module which processes these entities. No baseline generative models exist currently for direct comparison. Therefore, we designed our own baselines by repurposing existing generative architectures. The closest baseline are existing approaches which have semantic conditioning as input and output RGB images. We modify these to take category and part information as semantic conditioning input and output RGB object as shown above. Layout view originally generates object bounding boxes given an object list for a scene. Layout to translate object bounding boxes to RGB. We repurpose them as shown. We also set a baseline by replacing one or more of our original pipeline components with existing scene generation approaches. This graphics summarizes the baselines we set up for comparison. The diversity in our baseline configurations provide an opportunity to evaluate the feasibility of repurposing existing scene and single category object generation models for our problem setup, that is part-aware large-scale object generation. In terms of the popular quantitative measure FID, MeronymNet obtains best overall score compared to the baselines at a category level. The category condition version of SBGAN is seemingly better for some categories. However, MeronymNet's performance is especially superior for object categories with large range in parts and object geometry. This can also be appreciated from sample generations, and notice that our generations are closer in quality to real counterparts from the test set. Also note that SBGAN tends to produce blurry and disconnected objects. To conclude, we have presented MeronymNet, the first ever part and category controllable generative model for 2D object sprites. Our model generates diverse looking RGB object sprites in a part-aware manner across multiple categories using a single unified architecture. Via our evaluation, we have shown that scene generative models, even so dark, cannot be simply repurposed for object generation. In short, the seemingly reasonable analogy objects are to scene what parts are to an object does not apply here. This is because the geometric and photometric constraints for parts and objects are stricter compared to objects in scene. Check out our project page for code and additional resources. Thanks for listening.